Okay, let us continue the next question. So hexagon ABCDEF circumscribe a circle. Means you have got a hexagon. It is a six-sided figure. One, two, three, four, five, six-sided figure. Circumscribe a circle means the shape of the hexagon. It is the circle is inside the shape of the hexagon. Prove that AB plus CD plus EF is equal to BC plus DE plus FA. We have to prove this left hand side is equal to right hand side. So uh, we know the property of the tangent to the circle is if a circle is there, if this is the external point, then these two tangents will be equal. That is, suppose this is A and this is B, EA is equal to EB. This concept is being applied here. So what we are going to do, we are going to take particular points from each and every point. Suppose we start with the point A. So from A we have AR is equal to AM. From B we have BM is equal to BN. From C we have CN is equal to CO. From D we have DO is equal to DP. Then from E we have EQ is equal to EP. From F we have EQ is equal to ER. So what we are going to do, we are going to just write all of this. The solution start like this. That is, we can write from an external point, from an external point from a circle, the tangents are equal. The tangents are equal. So based on this, we are going to write the solution. How we'll write? Now we'll start with the from the point A. From the point A, we have AR is equal to AM. From the point B, we have from the point B we have BM is equal to BN. So where AM is there, there I will write BM. Here it is. BM is equal to BN. Okay. From the point C, we have CN is equal to CO. CN is equal to CO. From the point D, we have DO is equal to DP. DP is equal to DO. From the point E, we have EP is equal to EQ. From the point E, we have EP is equal to EQ. Then from the point F, we have FQ is equal to FR. FQ is equal to FR. See, why I will take FQ is equal to in the place of EQ. FQ and EQ I will keep in the same line because if I add FQ plus EQ, I should get the FE. Okay. After this, what we have to do? We have to now we have to see that take the left hand side, consider LHS, consider LHS. What is LHS? AB plus CD plus EF. Now what is my AB? Now what is my AB? AM plus MB. So I will write here AM plus MB plus what is my CD? CD is CO plus OD. CO plus OD. Then I have EF. EF. EF is EQ plus QF. EQ plus QF. Now I can see that I have to prove RHS. So what do I do? Let me search now RHS. What is RHS? RHS is BC. So if I write what is my BC? BC is equal to, see here, BC. This is my BC. BN plus CN. Yes, na? Then what is my DE? DE is equal to DP plus PE. DP plus PE. Then what is my FA? FR plus AR. FR plus AR. Now you see, we can group this now, where all we can find the sides where we have to rearrange them. Now in place of I want all this, I want AR, I want PE, I want CN, BN, DPN, FR. So can I substitute from here? Can I substitute this as in the place of AM I will put AR, in the place of MB I will put BN, in the place of CO I will put CN, in the place of OD I will put a DP, in the place of EQ I will put PE or EP, plus in the place of QF I will put FR. Okay. Now you check for all the terms here. I've got BN plus CN, BN plus CN, DB plus PE. So I've got DP plus PE. Then what is FR? I've got FR, I've got FR plus AR. So I can rewrite all these things in the form of, so what I'll write BN plus CN, BC. So I'll write in the place of this as BC. Then this one and this one together, AR plus FR, I will write it as FA plus FA. Then plus DP plus PE, I can write it as DE. So I will write this as DE. Rearrange the terms according to the right hand side. This will become BC plus DE plus FA. This is our RHS. Hence, proved. Okay, so this is the way you have to start the solution and end it up. Let us go to the next question. See in this, the tangent to the circumcircle of an isosceles triangle. So how we'll write now? ABC is an isosceles triangle. You know what is isosceles triangle? These two sides are equal. Which are the two sides equal in isosceles triangle? These two sides are equal. Given AB is equal to AC. You have to show that the tangent to this triangle at the point A is parallel to BC. You have to show that this tangent is parallel to BC. So now we know that we have to show that A is parallel to BC. So EF is parallel to BC. So what we have to prove? We have to prove that EF is parallel to BC. Now let us start the proof. How we will start the proof? The proof says like this. See, we have, now we know that these two sides are equal, it is given. So in triangle ABC, I have got AB is equal to AC. This is given. Okay. Then when AB is equal to AC, you know that the base angles also will be equal. When the two sides are equal, the base angles also will be equal. So what I can write? Therefore, angle B is equal to angle C. Angle B is equal to angle C, or you can write ABC is equal to ACB, because isosceles triangle property. In isosceles triangle property, when the sides are equal, the base angles also will be equal. Now from this you can take up from these two equations I can get this one. When I am telling AB is equal to AC, angle B is equal to angle C. When angle B is equal to angle C, angle EAB, can you see this angle? What you can say about this angle? EAB is equal to angle A EAB is equal to angle ABC. What is the reason I can tell this? This both angles are alternate angles. This angle and this angle, alternate angles, as well as this angle and this angle are alternate angles. So therefore, I can write it as, therefore angle EAB is equal to angle ABC, because alternate angles. Also here FAC FAC is equal to angle ACB. Again, these are also alternate angles. Therefore, what you can say, when the alternate angles are equal, then we can say that the lines are parallel. Therefore, EF is parallel to BC. So EF is a tangent drawn from passing through the point A of the triangle. So EF is parallel to BC because the alternate angles are equal. This is the alternate angle lines and angles. We have learned that when there are two parallel lines, when this both will be alternate angles, they will be equal. When two parallel lines is there and it is cut by the transversal, so they can tell that the when the alternate angles are equal, we can tell that the lines are parallel. So when I can tell this, these two lines are there, this one line cutting these two lines or intersecting these two lines. So this angle and this angle becomes alternate angles and hence these two lines are parallel. So we'll go to the next question. See in this one, you can see that if a number of circles touch a given line segment PQ, this is the circle C1. You can see that this is the circle C1 touching the point of contact A. This is the circle C2 touching the point of contact A. Circle C3, C4, C5 all are touching at the point A. The circles are denoted by S1, S2, S3, S and S4. So the question given is, we have to see that if a number of circles touch a given line segment PQ, PQ is a line segment, it's also a tangent at the point A, then their center lies on the perpendicular bisector of PQ. Means if this is a circle, if you have got this as a, if you have got this is a circle and this is a tangent, then he's telling that the circle's center will lie on the perpendicular bisector of this line. If a line is cut into exactly half, this line is called a perpendicular bisector. This line will make this line equal. So it is said that when such a case happens, the center of this circle lies on the perpendicular bisector. This is the perpendicular bisector of this tangent. So we have to prove that. So what we are going to do now, we just write solution. S1, S2, S3, S4, S5 are circles with the C1, C2, C3, C4, C5 as the centers respectively. Then PQ is a tangent to the circles at A. Okay. Then we can tell at the point A, C1 is perpendicular to PQ, C2 is perpendicular to PQ, C3 is perpendicular to PQ, C4 is perpendicular to PQ. Then this all the C1, C2, C3 lies on the perpendicular line to PQ. These centers C1, C2, C3 they all lie with the centers of the circle. They lie on the perpendicular bisector of the line PQ. Therefore, they lie on the perpendicular line perpendicular line to PQ, but not on the but not on the perpendicular bisector as PA. May or may not be equal, may or may not be equal. This is may or may not be equal to AQ. Means we need to say that this no doubt these are all perpendicular to PQ. These are the lines, these are the centers. C1 is a center. From there you draw perpendicular to PQ. C2 is a center. From there you draw perpendicular to PQ. From C3 center you're drawing perpendicular to PQ. So it is not necessary that this can be lying on the perpendicular bisector, as means may or may not. This distance may or may not be equal. So the AQ on and the PA both may or may not be equal. Next, we have got this question. Next question. XP and XQ are the tangent from X. From X you have got XP tangent. From X to XQ we have got the tangent. Now we have to prove that this one we have to prove. So according to this question, we know we will start the solution. R is a point on the circle. R is a point on the circle such that XA, XA plus XB, XA, this is XA plus AR. Let me draw this with the red one. This XA plus AR should be equal to XB plus BR. We have to show that. So let us start with this now. Let us start the proof. Okay, the proof says we know that X is an external point. X is an external point to the circle, to the circle. Therefore, XA is equal to XB because the tangent drawn from an external points are equal. Tangent is XP and XQ. So therefore XA is equal to XB. Okay. But we know, but what we know? But we know that what is XA? What is X? It's a part of the tangent. So, but XP is the tangent to the circle is equal to XQ. That is also a tangent to the circle. These are the tangent at the point of contact P and Q. So XA is a part of the tangent, XB is a part of the tangent. This will come to the next step. So XB is equal to XQ we got. That is because the external point, the tangents are equal. But what I'll write in the place of XP? XP is a combination of XA plus AP. So I will write this as XP is equal to XA plus AP. Then XQ is equal to this XQ is equal to XB plus BQ. XB plus BQ. So here we got, but we know from here you see this point A. If we consider this point A, AP is equal to AR because A is the external point. From point B, BQ is equal to BR. So let us write this. From point A to circle, AP is equal to AR, and from point B, BQ is equal to BR. The reason is A and P are A and B are external points from which tangent is drawn to the circle, from which tangent is drawn to the circle. Now, when we know that this one is there, here what we can do, we can just change this now, you see. From this is equation, let us name as equation 1. Therefore, in the place of xp, can I put it as AR. Therefore, equation 1 becomes XA plus AR XA plus AR is equal to XB. Here I will write XB as it is, plus in the place of BQ I can write BR. So BR. This is how we got the relation XA plus AR is equal to XB plus BR. Next question. Two tangents are drawn here. So see, these two tangents are drawn. TP and TQ are the two tangents with an external the center point O. Prove that PTQ, this angle T PTQ, this angle T is equal to twice OPQ. Twice OPQ. This is your OPQ. So what I have to show? I have to show that angle PTQ is equal to twice OPQ. This one we have to show. This is to prove.